All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for physical science. And today we're going to be picking up where we left off by introducing the first type of chemical bonding that you're going to encounter in this class, and which what we've been able to observe in nature itself. And so that first type of bond is what's known as an ionic bond. And you might even notice that even within that name, you see a word that we have seen before. We see the word ion, right? So that's going to let us know, going to give us a hint that, okay, if we're talking about an ionic bond, we're probably going to be dealing with substances that have ions in them, and that'd be absolutely correct. So an ionic bond, what it is, like we talked about, there's an attraction, there's a force that's acting on two ions here that are oppositely charged. It's going to cause them to come together and to become chemically stable. So it's an attraction between two oppositely charged ions. Now, if you're thinking about it from the perspective of how ions form, we know that cations form when an element loses electrons or transfers an electron, and anions are formed when something gains an electron. So that's what we're going to be looking at here. Now, this is going to be formed by transferring of an electron from an element that's a metal to a non-metal specifically. That's a very broad classification that we can use, but it's a good first indicator. If we just look at, let's say, a chemical formula, if we were able to look at that formula and we see that we have a metal and a non-metal, more than likely it's going to be an ionic compound or an ionic bond that's holding those two elements together. And in that case, the metal element would transfer its electron over to the non-metal. Now, let's look at an example. So it's one thing for me to talk about it. Let's talk about an example. So we've got listed here the compound sodium chloride. Okay, now here's what's going to happen, right? We've got the element symbols even listed here. We've got sodium atom, which is in red. We've got the chlorine atom that's in black. Now, we've drawn the Lewis structure, and we see that sodium has one valence electron, and we see that chlorine has 7. Now, if we think back to the octet rule, what we know needs to happen is that sodium, if it loses one, it goes to an octet, and if chlorine gains one, it gets 8 electrons in its valence shell, and it gets to an octet. So what happens is that sodium is going to give an electron, I'm using the term give very loosely here, to chlorine. Now, as a result, when sodium loses this electron, right, its number of protons stayed the same. It now has one less electron, so it becomes positively charged, becomes a cation. And then the chlorine, because it gained an electron, its number of protons stayed the same, its number of electrons went up, and so now it's a negatively charged ion, it's an anion. So in our final kind of structure over here, you're going to have sodium ion and chloride ion that are being held together by the fact that sodium is positively charged and chloride is negatively charged. And so once that happens, those positive and negative charges, they attract each other. And so the result of that attraction is that chemical bond, that ionic bond between those two ions. And so then we get an entirely new compound that's now sodium chloride. It's no longer just sodium chlorine, it's sodium chloride. And it's going to have its own unique physical and chemical properties that might vary when looking at sodium or chlorine individually. Okay, so this is what's going on in that particular process when a bond is being formed. Now, another way to think of this is to look at it from the perspective of its Bohr model. So we've looked at previously in Bohr diagrams how it can show us all of the electrons and their energy levels, right? And if you remember, we talked about how the first energy level was able to hold 2 electrons, and the other levels, at least for our purposes, we're going to say hold 8. And the electrons that are in the outermost shell are going to be classified as the valence electrons, right? And so if you're following along with this little animation here, we can see that sodium has 3 rings and chlorine has 3 rings because they're both on the third period on the periodic table. Remember, third period means third row. Now, what we see happening is that sodium's 1 valence electron ends up transferring over to that final energy level of chlorine in this spot where there's not a pair. And when that happens, we see that sodium goes from being neutral to being a positive charge. Chloride becomes negatively charged. Energy gets released. Then they come together and they form their bond. And we can see it now as they're overlapping and getting this interaction between the positive sodium ion and the negative chloride ion. Okay, so it's just another way for us to represent and visualize what's going on when an ionic bond is being formed. Here's another example. So we've got lithium and bromine. Lithium is in group 1. It's one of our alkali metals, which means it's in the first column on the periodic table. And then bromine is a halogen, which means it's in column 17 or 7A on the periodic table. So again, we've got a lithium atom, bromine atom. Lithium has 1 valence electron, bromine has 7. So lithium is going to want to give or transfer its electron to bromine. When it does that, lithium becomes positively charged. The bromine, because it gained an electron, it's now no longer bromine, it's now bromide because it now has 8 valence electrons. And so when this happens, we now have the formation of no longer it's not lithium bromine, it's now lithium bromide. Okay, and something that you might have noticed looking at the past 2 compounds, we had sodium chloride and we had lithium bromide. And actually, that's not correct. That should say bromide. And you might have noticed that in each of those cases, the ending for the second substance changes. It goes from INE or whatever it is to IDE. That's going to be something that's characteristic when we start to look at bonds, is that our substances, specifically the second substance, is always going to change from having that INE or whatever its name is to an IDE ending. So just something to be aware of that we're certainly going to revisit when we start talking about nomenclature. Okay. Now, how do we know the number of electrons that are being transferred? How do we know the charges of these compounds? Like, how do we know that lithium is going to be +1? How did we know that bromine was going to become a -1 charge? Well, if you remember, we talked about oxidation states in our periodic table unit. And so oxidation number or oxidation state simply is the charge on an ion. And it's going to indicate the number of electrons that need to be gained or lost in order for that substance to become stable. Now, if you notice, what I've done here is I've already kind of written on here the charges that are going to be most common for elements in their respective groups, in their respective columns. So we can see here, like for example, for group 1, the most common charge for the group 1 elements, so starting from hydrogen and going all the way down to francium, is going to be +1 or 1+. Right? So that means that lithium, sodium, potassium, rubidium, cesium, and francium all want to lose 1 electron. For the second column, we see that it has a 2+ charge, so that means that all of those elements want to lose 2 electrons. All right. When we start to look at the elements that are in purple, we skip those. We come over here. We look at column 13, and we're looking at specifically aluminum, gallium, indium, and thallium. We see that those metals will form a 3 plus charge. They're going to lose 3 electrons in order to become chemically stable, right? We can look in the next column over the elements that are germanium, tin, and lead. They tend to form +4 charges, meaning they lose 4 valence electrons in order to become chemically stable, right? And then when we start to see a shift, that once we get to column 5A, there's a shift. No longer are we starting to lose electrons, they shift over and start gaining electrons. So for nitrogen, phosphorus, and arsenic, we see that what's going to happen is that they're going to gain that number of electrons. So you've got a 3 minus charge, meaning nitrogen, phosphorus, arsenic, gained 3 electrons. Okay. When we look at the next column over, oxygen, sulfur, selenium, and tellurium, they're going to gain 2 electrons, right? And then the final column here, they're all going to gain 1 electron. And then our noble gases, they're just going to have a charge, or they're not going to form any charge because they're already stable. Now again, I've already said many of these things, and I'll just kind of repeat them real quickly. Noble gases, they're already stable, so they have an oxidation number of 0. Our elements with low numbers of valence electrons, so elements in column 1 and 2, want to lose electrons to become positive, right? And elements that have high oxidation numbers, 6 or 7 respectively, 6 or 7 valence electrons want to gain electrons, all right? And so, like from this video, I would certainly go back to that previous slide. If you need to, pause it, look at that again, kind of walk back through what I talked about so you can know when you're looking at these elements, what charge do I know that it's going to form based on just this predictable pattern? Okay. Last thing I want to talk about is the structure. Like, what do ionic bonds, what do they look like? Like, if we could look at it at an atomic level, what do we get? And what we see is that for when ionic bonds are formed, we get a 3D crystal lattice structure. So 3D meaning it's just 3-dimensional, right? And crystal lattice is just communicating that it has a very specific and repeated pattern, okay? So crystal lattice, I want you to think repeated pattern or arrangement of ions, right? So in our ionic substances, when you start to look at how they're structured, there's going to be a very specific repeated pattern or arrangement of the ions within that solid structure, right? And so the placement of those ions, they are important. They're not just random. It results in a regular repeating arrangement. And ultimately, this is going to give the compound structure. So it's what's going to allow for it to become a solid. Because when we look at ionic compounds, they're typically solids at room temperature. And that's because they have these repeating 3D crystal lattice structures. Again, it's one thing for me to talk about it. Let's actually take a look at a picture. And so here are some examples. We've got the crystal lattice structure of sodium chloride, and we also have the crystal lattice structure of silver 1 bromide. And so as you can see, there's a defined pattern where the sodium atoms, for example, are surrounded, or sodium ions are surrounded on all sides by a total of 1, 2, 3, 4, 5, 6, 7. It looks like, what is it? 1, 2, 3, 4, 5, 6. Should be 6 chloride atoms on each side. And so because of that structure, it makes it very stable. And that's what they would look like in the solid state. So that's all I've got on ionic bonding for today, ladies and gentlemen. Thank you for watching this. Feel free to watch this again. Feel free to bring questions to class if you have any. And I look forward to seeing you guys again soon. Thank you so much, and take care.